Imagine a bucket full of water. If the bucket is upright, we know the water remains at the bottom of the bucket. We also know that if we were to flip the bucket upside down, the water would fall out. Now picture a bucket of water swinging in a vertical circle. Notice that as this bucket turns upside down, the water remains in the bucket. So why does the water remain in this bucket as it rotates upside down? For a circular motion, we know that the net force of an object will always be pointed towards the center of the circle. When the bucket of water is at the bottom of the circular motion, its centripetal force, represented by mv squared over r, is equal to its normal force minus its weight force. And conversely, when the bucket of water is at the top of the circular motion, its centripetal force is equal to its normal force plus the weight force. Let's imagine that the velocity of the swinging bucket were to decrease enough so that the centripetal force was equal to the weight force. The object would still be able to complete the circle, but the speed at which the normal force is equal to 0 is the absolute slowest speed at which the bucket of water can complete the circle. So if the radius of our circular motion is 1.09 meters, the slowest speed at which the bucket of water can travel is approximately 3.27 meters per second. In calculating the velocity at which the bucket of water is traveling, we determined that the period of time it took the bucket to complete one rotation was 1.4 seconds, which led to the bucket's velocity being approximately 4.9 meters per second. This concludes that if the velocity of the bucket was less than 3.27 meters per second, the water would fall out as it rotates to the top. And if the velocity is greater than or equal to 3.27 meters per second, then the water remains within the bucket throughout the full rotation.